Hello, we are the Go Volts team from Lincoln Pius X High School in Nebraska, and we'd like to thank you for taking the time to review our presentation for the 2016 and 2017 SMART competition.
So our agenda for today, we will be going over our baseline simulations that we ran, our economics, our zone considerations, building materials, our HVAC systems, our building orientation, and our roof comparisons, as well as shading considerations, our final simulations, our site considerations, our power generation, and finally our conclusion.
I'm Taylor Geirhan.
I'm Kathleen Medill.
I'm Tom Fulton.
And I'm Natalie Schieuer, and our teacher is Mr. Scheffler.
So for this project, we were given a school and a gymnasium, and our goal was to redesign them so that they were both energy efficient and constituted an intelligent building design.
And so as a team, we decided some of our goals would be to make our building cost-effective, energy efficient, and have a reliable design. So we decided that we would lower the cost of our gymnasium, lower the energy consumption, and increase the reliability. And one other thing we decided was to measure whether or not we met these goals was we would use the energy simulator in the simulations we ran to see if we met these goals. And so we decided to look at the economics report, the amount of set points not met, and also the energy consumption within these simulations.
So we ran our baseline simulations, and after running our baseline simulations, we found that cooling composes almost half of all the energy consumption. So we decided to focus our efforts into minimizing the amount of energy spent on cooling.
And it was important to us to reduce the cost of the gym. And we found out through the baseline audit that the total cost of operation was per year about $39,000. And the way we were wanting to reduce this is by using different building materials and HVAC system.
So when making modifications to building materials, it's important to consider which climate zone your building is located in. So our school was located in Raleigh, North Carolina, which is in Wake County. Wake County is part of Zone 4. So when making modifications to the materials, we used materials that were appropriate for Zone 4.
And so after running many different simulations and comparing these to our baseline energy audit, we were able to decide which materials would decrease our cost and energy consumption. And we also kept in mind the R value of the insulation materials we use, keeping in mind that a higher R value means better insulation. And so after running simulations, we compared them to the baseline energy audit and used the following materials as they decrease cost and energy consumption the most. So for our roof, we use what is known as attic with metal deck, steel joist, non-residential in 2004. For windows, we use 40 to 50% glazing, fixed, all orients, non-residential 2004. And then for our walls, we use 12-inch heavyweight concrete, that insulation and gypsum board. And then for the insulation and the partitions, we use dense plastic, half-inch dense concrete block, and 8.5-inch dense plastic. And then for our lighting, we wanted to use LEDs as this was recommended by the engineers we consulted, as it was cost-effective, energy efficient, and reliable. But unfortunately, this was not an option in the energy simulator. But we did find compact fluorescent lights were comparable to LEDs in their efficiency and longevity, and were an option in the energy simulator. So we decided to use compact fluorescent lights. They were also superior to incandescent lights, which were the default option in the energy simulator.
So after deciding building materials, we decided to look at the HVAC economics. So we compared HVAC systems with our baseline energy audit and found that each HVAC system with building modifications has actual lower costs than the baseline energy audit itself. We found the water source heat pump has the lowest annual cost for the systems we were able to choose from and decreased the cost by over $8,000.
And next, we looked at the total site energy consumption for each HVAC system. And each HVAC system with the building modifications had a lower total site energy use than the baseline. And the water source heat pump was the lowest annual total site energy use, and it decreased the baseline's energy use by about
why we decided to go with the water source heat pump.
And so we still wanted to further look into this water source heat pump to look at the set points not met. So we constructed a graph of the amount of set points not met per month by the water source heat pump. And one thing we considered was when the gym would be used most often. And so we decided that the gym would be used most often during the fall and winter during the prime of basketball and volleyball season. And so we really focused on those seasons when we were looking at the amount of set points not met. And while looking at the graph throughout the whole year, the water source heat pump minimized the amount of heating set points not met, so they were almost negligible. As you can see, there's very few amount of area that is red on the graph. And then when we focus on the fall and winter, as you can see here, there's very few set points not met. And the majority of those cooling set points not met occur from May to September when the gym would not be used as often. And so since we were focusing on the fall and the winter, we decided that the water source heat pump would really be a great option to meet those set points when the gym would be used most often.
So with the water source heat pump, in conclusion, it's the lowest cost, it has the lowest amount of heating set points not met, and the lowest total site energy used, and was highly recommended to us by 3 engineers and our research. So we decided to use this for our gym.
So after we finished deciding on the building modifications to materials and the HVAC system, we decided our next step was to find the optimal orientation for our building. And our definition of optimal orientation is the orientation that gets the roof the most amount of solar exposure. And to find this, we used the building designer, and we found that 0 degrees was the optimal orientation.
So next, we decided to compare roof types to also optimize the solar exposure on our roof. So we ran yearly solar exposure simulations for each of the 4 roof types and found that roof type number 4 was the best for our design.
And so we found that there were several advantages of having orientation at 0 as well as having roof type number 4. We found that this maximized the solar exposure for our gym. Through our solar exposure calculations, we found that the gym would receive 4,435.32 hours of solar exposure per year, which when we calculated this was an average of 12 hours per day of solar exposure throughout the whole entire year. And choosing roof type number 4 was also a good choice for solar panels, as the sloped roof provided a good angle, and it was also a large area for an easy installation of solar panels. And this angled gym was better than a flat roof, because when we consulted with a local engineer, he told us that often you want the solar panels sloped instead of having them flat to maximize solar exposure, and thus it allowed for an easy installation because the roof was already sloped. Thus you would not need a mounting system to slope the solar panels. And we also noted that the roof type number 4 at orientation at 0 degrees was very consistent throughout the entire year. Shown in the left part of the screen is a solar exposure calculation for the winter solstice of 2017, which is the darkest day of the year. And even on the darkest day of the year, our gym would still receive 9 hours of solar exposure. And thus we decided to use roof type number 4 and orientation at 0.
So after looking at building orientation for solar exposure, we decided to consider shading. So we looked at different window shading options in the building designer and ran solar exposure calculations. We found that window shading option number 1 not only minimized the amount of sunlight that penetrated along the walls and windows of our gymnasium, but it also reduced the amount of cooling needed for our gym.
So after finalizing all of our choices, we ran a final simulation. And as you can see, our final simulation with the water source heat pump is shown by the top bar in both graphs. And it's actually the smallest bar in both graphs. And that made us really excited because that meant that the water source heat pump was not only the most cost effective, but also used the least amount of energy.
After making these changes, we considered a few other site modifications, such as an energy recovery ventilation system, wind energy, solar panels, trees, and a building management system.
So we decided as a team we still wanted to further decrease those cooling costs, and so we consulted a local mechanical engineer who directed us to energy recovery ventilation systems. And after researching these and consulting the mechanical engineer, we found that energy recovery ventilation systems allow for controlled ventilation, which helps to decrease the energy loss. And so we continued to research ERVs, or energy recovery ventilation systems, and found that they decrease the summer cooling costs, decrease the winter heating costs, and also decrease that summer humidity. And further research showed us that ERVs, they recover 70 to 80% of the exiting air and input this energy from that exiting air into the incoming air, thus recycling that energy to allow for a energy efficient and cost-effective ventilation. And so in summary, an energy recovery ventilation system would allow us to decrease our heating and cooling costs and allow for a cost-effective, reliable way for ventilation to occur.
So after researching our ERV system, we looked at wind energy, and we initially considered the use of wind turbines on our gymnasium, but after reviewing a wind rose of Raleigh provided by the State Climate Office of North Carolina and consulting our engineer, we determined that the amount of wind in the area was insufficient to outweigh the cost of installation of wind turbines. So we decided to continue our research in other areas. We also, after talking with local engineers, found that wind turbines in the city are not only not efficient, but they're also, they cause things like noise pollution, and they just don't produce enough energy to be considered efficient in our building.
So after looking at the wind energy, we started looking towards solar panels. And we actually consulted an engineer who's an expert on solar panel systems. And he actually recently had finished installing his own personal solar system. And reasons why that would be good for our gym is, again, like Natalie said before, the sloped roof allows for easy installation. And it's also really exciting, innovative technology, and it'll bring money in as well as save energy. And along with that, our school is a commercial building, which means we will most likely receive some government funding, which will decrease the amount of cost a lot. And most importantly, it's a green option that is not harmful to the environment.
Another thing that we discovered while researching solar panels was the Swanson effect, which describes the dramatic decrease in price of solar panels since 1977. In 1977, the cost of solar panels was $76.67 per watt, and that's been reduced dramatically. In 2013, the price of solar panels was just 74 cents per watt. So this further confirmed our choice in using solar panels for our gym.
And so we continued to research the use of solar panels, and especially specifically in North Carolina, where our gym is located. And we were excited to find that the cost, or that solar panels will pay for itself. And eventually in North Carolina, the average solar system will pay for itself within 13 years. And we're excited to find that this was lower than the national average as well, so that it shows that North Carolina is a great state for solar panels, thus confirming our use of solar panels for our gym.
So we looked at the cost for our solar panels. Found the average cost to have solar panels installed in North Carolina per year is about $13,896, which is lower than the national average.
And then the annual savings. Solar panel systems can actually save a lot of money, and the average annual savings for North Carolina is about $21,000, and that's higher than the national average. And it's also higher than the cost.
So to get a more specific idea of what our solar panel system could do, we used the PV watts calculator. This is a free estimator run by the National Renewable Energy Laboratory as part of the U.S. Department of Energy. So it estimates the amount of energy produced and the cost of photovoltaic systems. So to ensure accurate results for our system, we input local weather data and the dimensions of our roof.
And so shown here on the slide are the input data and the output data for our PV watts estimate. And as you can see by the red circles, our estimated solar panel system output would be 210 kilowatt hours per year with an annual energy value of almost $17,000.
So here are some graphs of the cumulative energy produced per year and the cumulative energy value. As you can see, in 20 years, the amount of cumulative energy produced for the photovoltaic array is over 4.2 million kilowatt hours of energy, rated at a cumulative energy value of over $300,000.
And along with solar panels, we thought trees would also be a great thing to have because not only does it add natural beauty, it can also provide shade and many comfortable places for students to hang out at. And it also benefits the environment, and we learned in the Smart Competition Guide, we were all actually really intrigued by this. Trees absorb approximately 25 pounds of carbon dioxide per year. And so we researched the types of native trees to the Raleigh area, and we found that the Japanese maple was the optimal tree because, first of all, it grows well in the Raleigh area, and they also don't get very tall, so they wouldn't get in the way of any of our solar panels.
As part of our further research, we looked at the Bullitt Center, which is a green office building in Seattle, Washington. So the Bullitt Center uses a building management system known as BMS, which is a computer system that automatically audits the conditions of the building and then adjusts the systems accordingly. For example, in mild temperatures, the BMS will automatically open the windows to cool the building naturally. And then when the temperature becomes too cold, it will automatically shut the windows to retain heat. So as a group, we decided that we would like to use a BMS in our building. So the BMS would be able to open the windows in mild weather to get some circulation and help with cooling. And it would also be able to monitor the set points not met and adjust our HVAC system accordingly. We also decided, however, we'd like to maintain the option to manually override the BMS.
One other important thing for us to consider was how we were going to generate power. And this was especially important because we had chosen to use solar panels, so we needed to decide how we were going to use these solar panels to generate power. And so we consulted the local engineer again, and he directed us to the Bullitt Center, which again is the green office space in Seattle, Washington. And this Bullitt Center was an important resource for us as they have 575 solar panels on their roof. And we further researched the Bullitt Center and found that they connect their solar panels to the Seattle power grid. And so we decided to employ a similar system within our own gym. So in our own gym, we would connect our solar panels to the Raleigh City power grid. And then in the summer, when we produce a surplus amount of energy from our solar panels, we would be able to sell this surplus of solar energy from the solar panels to the Raleigh City power grid, and then thus be making money during the summer. And then in the winter, if there's a deficit of energy produced by our solar panels, we'd be able to purchase energy off the grid from the Raleigh City power grid, and then be able to ensure that we are meeting those electrical set points in our gym. And we were really excited about this system because it meant that we could be earning money from our solar panels while at the same time maintaining those electrical set points of our gym.
So in conclusion, we learned a lot from this competition and are actually very happy with our results. Our annual savings from changes made to the HVAC and building material systems is $8,263.06. We reduced our total site energy by 214,934 kilobtu's, and our solar panels annually produced 717,453.96 kilobtu's and an annual energy value of $16,737. So overall, we met our set points. We met goals of decreasing cost and energy use, and we increased the reliability of our gym design. Thank you.
Thank you.